All right, everybody. So I hope you're doing all right. Today, what we're going to do is we're going to look at continuing our orbital mechanics unit here. And what we're going to look at today is kinetic and potential energy. Now, some of you have probably had physics. You've seen this before. So the equations that we're going to look at here probably are not too much of a surprise for you. So kinetic energy, we'll start there. Kinetic energy is the energy an object has because of its motion. Now, like all the other forms of energy, we're going to measure this in joules. The faster an object's going, the more kinetic energy it has. So an object that's stationary, in theory, has zero kinetic energy. As it goes faster, it has more and more kinetic energy. And you'll notice that kinetic energy actually is relative to velocity squared. And our equation here is 1/2 mass of the object times velocity squared gives us kinetic energy. Now, this is all well and good, but a lot of times it's hard to know exactly what the mass of an object is just by observing it. Or if you're in a spacecraft, you don't know exactly how much fuel's been burned or, how many pounds of moon rocks you're carrying or anything like that. So a lot of times what we look at is we look at how much kinetic energy per unit of mass we have. So we divide both sides by mass, and then all we need to calculate is just our velocity. So it's 1/2 velocity squared equals kinetic energy over mass. And what this would be is you'd say something like, we're going, let's say you have a velocity of 4 meters a second. So you'd say 4 squared is 16, 1/2 of that is 8. So what you'd say is we have 8 joules per kilogram of mass. So if I have something that's going those 4 meters per second and it weighs 3 kilograms, it would have 24 joules of energy. Or if it had 10 kilograms of mass and it was going 4 meters a second, we would say that it has 80 joules of energy. But we base this relative to the mass, like you see here. So we just say that it has a certain number of joules for every kilogram of its mass. So then we can calculate it knowing only the velocity, which is easier to find orbitally. Here's an example. So here's a ship from Kerbal, and this is from the map screen. Remember, you just press M to get to the map screen. And what we see here is this ship is traveling at a velocity of 2191.9 meters a second. So we're just going to call that 2192. And I don't know the mass of the ship, but I don't need it because I'm just going to say, what is our amount of kinetic energy per kilogram? I can take this number and plug it in. So I'll say 1/2 of 2192 squared. And that gives me about 2.4 million. And my unit here, since I'm looking at energy per mass, is going to be joules per kilogram. The second thing we want to look at is potential energy. Objects have energy not only because of how fast they're going, but they have energy because of their position. So for example, if I had an object and it was sitting on the floor, that object has nowhere else to go. All right. So it has no energy. It can't spontaneously start to move. However, if I had an object and I was holding it at the same height as my head and I let go of it, since it has that potential energy, that gravitational potential energy, now it spontaneously begins to move because it's being accelerated by the Earth, and that energy pulls it down. So this potential energy is how much energy an object has because of its position above ground level. Now we calculate this. Potential energy is relative to the mass of the object. The more mass something has, the more energy it can have as it falls. G, this is the gravitational value. This is about 9.8 meters per second squared or 32.2 feet per second squared, depending which unit we're using. And the height of the object, that's the H there. So just like kinetic energy, we're going to write this relative to its mass. So we're going to divide mass out of both sides, and we're going to say how much potential energy does it have for each kilogram. And when we divide it out, we find potential energy over mass equals the gravitational constant times h. Now we call it the gravitational constant Well, it's only constant as long as you're on the Earth's surface, which is all well and good for most things you're doing in physics. Not very good for things you're going to do with orbits, because you're never on the Earth's surface, basically. So, as we get further from the Earth, the gravitational pull of the Earth actually becomes less on the object. So this G value is not constant. So we actually have to find it, and it can vary quite a bit. So let's look at how we do that. So we can calculate G. Our G value is relative to our distance from the center of the planet. So, for example, these R values here are radiuses. They're measured from the center of the planet. Notice, not the surface of the planet, but from the center of the planet out to where the object is. The ratio between those is the same as the ratio between the G values, except we have to square the distances out here. And this actually goes back to the universal gravitation equation. We're not going to go into that, but if you've had physics, you're familiar with it. Remember, the gravitational force is m1 times m2 times big G over the radius squared. That's actually why this ends up being squared. So when we see R1, R2, G1, G2, what do the 1s and 2s mean? The 1 basically just means on the surface of the planet, and the 2 means somewhere else. Usually for us, that's going to be an orbit, although in theory, you could also dig a hole deep enough that you change your G value and gravity would get stronger. So the 1 is pretty well known, and these won't really change for us. The 2 values are going to be our variables here. So what we're really trying to find is what this G value is when you're at a certain height. That's our G2, because G1 is what the G value is on the ground. G2 is what the G value is when you're at a certain altitude. So we're going to solve the equation for G2. We just multiply both sides times G1. So we'll find G2 equals G1 times the ratio of R1 over R2 squared. Now we know R1, that's the distance from the center of the planet to where you are when you're on the surface. So that's just the radius of the planet itself. That, of course, depends on the planet. And the G value also depends on the planet. The people that made Kerbal, they made the G value for the surface of Kerbin and Earth actually the same. It's 9.81. So this G1 for us, as long as we're dealing either with Earth or Kerbin, is always going to be 9.81. For Kerbal, the Kerbin radius is the surface of the planet right here. The R1 is 600,000 meters. For the Earth, it's different. It's significantly larger. All right. Notice, since it's squared, this decreases geometrically. If I double this distance, so I've gone from 600,000 to 1.2 million meters. This becomes a half, and when I square it, it becomes a fourth. So if I double the distance, I have 1/4 the G value, 3 times the distance, 1/9, etc. And you see how it drops off geometrically there. So let's do an example here. Let's say that we are in orbit and we are at 1,500 kilometers. All right. So let's plug in what we know. We know the G1 value on the surface of Kerbin is the same as Earth, 9.81. We know that the radius on the surface of the planet is 600,000 meters. And the second radius, you're wondering where we get this 2.1 million number from. Well, 1,500 kilometers is 1.5 million meters. But remember, when we're measuring altitude, we're measuring from the surface. When we're using this equation here, we want to measure from the center of the planet. So we have to add on the actual radius of the planet to that, because this 1,500 kilometers gets us from where we are in altitude to the surface of the planet. Then we have to add that other 600,000 meters to get from the surface of the planet to the center of the planet. So 600,000 meters plus 1.5 million meters gives us this 2.1 million meters. So 600,000 over 2.1 million, We'll find that number, we square it, and then we'll multiply it times 9.81. And what we find is the gravity that far from the planet is actually only 0.8 meters per second squared. It's less than 1/10 the gravity at the surface. Gravity actually drops off pretty fast as you move away from things. So if we want to put this all together and find potential energy in orbit, here's the same picture as before. And this time we're really concerned about this altitude. So the altitude here is 130,840 meters, we'll say. So I want to find the values here. I know my G1 is that 9.8. My R1, that's the surface of the planet, it stays 600,000. Now I want to find my R2. This is my altitude. Remember, I want to make sure I add that to my radius of the planet. So 600,000 plus 130,840 to get my 730,840. That will be my R2. It will go down here. And I'll find that my gravity value at this altitude is only 6.61 meters per second squared. So that's the value I'm going to be using. Now I want to find what is my potential energy for each kilogram. So my potential energy per mass of the ship. So I need the G value and I need the height. So my G value, we had just found, that's 6.61. And the height, we're measuring potential energy from the surface of the planet now. So my potential energy is my height is 130,840. Notice height relative to the surface, my radius relative to the center. So those are the differences between the H and the R's. So when I multiply this all together, I can find what is my potential energy per kilogram. All right. So this object has a potential energy because it's in orbit, and it has a certain amount of kinetic energy because it's moving. So it has both. Now, how do those work together? So our law of conservation of energy tells us that the total amount of energy has to stay pretty much the same here. Not even pretty much the same, it has to stay the same. We can change from one type of energy to another. And as long as we're not undergoing nuclear fusion, the energy isn't going to convert to mass or anything like that. So we don't have to worry about that. So here's a couple ways we can transform potential energy, can turn into kinetic energy, and kinetic energy can turn into potential energy. They can switch back and forth. And it's not permanent. Once one switches to the other, it's not stuck that way. It can shift right back. For example, if I have a ball rolling on a surface and I have a little dip in the surface here, the ball can be relatively higher and it's rolling along, let's say fairly slow. And when it hits this little dip, what's going to happen is as it rolls down the dip, it's going to accelerate. Now, since it's accelerating, it's going faster. What that means is our kinetic energy, our energy of the speed of the object, increased. See here, our kinetic energy was low, it's going slow. Here, our kinetic energy is high because it's going faster. Where did that energy for the ball to speed up come from? It came from the transfer of potential energy. Here, the ball was higher up, so it was further from the ground. It had a higher potential energy. In this situation, the ball is closer to the ground, so its potential energy is lower. So the ball's rolling, it goes down this dip, and then it comes back up. And what's going to happen when it comes back up? Well, it's going to slow back down because just like some of that potential energy converted to kinetic energy, when it goes back up, the kinetic energy is going to transfer back into potential energy. So we go from high and slow to low and fast and right back to high and slow. And we can see the energy transfer both ways, potential to kinetic and kinetic to potential. We actually see the same thing in orbits. So let's say this little blue dot is a spacecraft here. It's very high up there. Its distance from the center of the planet is pretty far. So that's a higher height. And since it's higher, it's going to be going slower. More of its energy is in gravitational potential. So it slows down. Then, as it comes around the orbit, if it has a fairly eccentric orbit, it will get pretty close to the planet down here. And what we'll see is since it's closer to the planet, it has a lot less potential energy because its height is much lower. since it has a lot less potential energy, where does that energy go? It can't just disappear. It has to change into something else. So what it changes into is kinetic energy. So even though the object is much lower, it has the same amount of energy. It's just not potential as much, but more kinetic, so the object goes faster. So in an actual orbit, you see the object, it'd go up here and be like nice and slow, and then come around and go woof. So nice and slow, and then whoosh, and then slow, and faster on that end, slow, faster on this end. And we actually see this in all types of orbits. Not only do planets do it, the parts of their orbits that are slightly closer to the sun, they go faster. But we also see this in comets and spacecraft and satellites. This is really common and seen in every type of orbit. The important thing to remember, though, is that the total energy in the orbit stays the same. Here, we have more potential, less kinetic energy. Here, you have more kinetic energy, less potential. But if I add them together, if I add up the total energy at any one point, the potential plus the kinetic energy here, and the potential plus the kinetic energy here, those numbers should be pretty much the same. All right. Now, how do we change this? Well, you have to apply energy to the system. So if I fire prograde, I'm going to add energy to my orbit. So I'm either going to make part of it go out higher, or I'm going to make part of it faster, or both most likely. Or if I fire retrograde, I'm taking energy away. The rocket's actually burning against your direction of motion, and I'll either make you go slower, or it will make you go lower. And we'll do one of those two. So the rockets will change the total amount of energy, and then it would redistribute itself between potential and kinetic as the orbit dictates. All right, so that's what we wanted to look at today. There is one last topic, and I just wanted to throw it in there. We are getting ready to do some more complex missions, so I wanted to look real quick at aerobraking. Aerobraking is basically just another energy transfer. Basically, what you're doing is when you're orbiting a planet, you're coming in at an angle where you're catching the atmosphere, and you're using that atmospheric drag to slow you down so you can come in either to land on the planet or just slow you down to establish a different orbit or something like that. This is just another energy transfer. However, instead of it being kinetic and potential, you're taking the kinetic energy here, the energy of the motion of the spacecraft, and using the friction with the air in front of it to heat up both the air and the spacecraft. And you're actually converting that kinetic energy to thermal energy. And since that thermal energy doesn't really affect the motion, you're just taking energy out of it. It's almost like firing a rocket in retrograde. So it takes energy away from your orbit. It helps you to slow down. And if you slow down enough, gradually then your orbit will fall back to the planet and you can land. Sometimes you do this in multiple cycles. They'll come around once and catch the very top of the atmosphere and slow themselves down a little bit. And the next time you go a little bit deeper into the atmosphere and it slows down a little bit more. And over a couple cycles, around a couple orbits, they'll land. Sometimes you can do it all in one shot. One of the big things is, whether you're going to do this in Kerbal or in real life, you definitely need a heat shield, because without a heat shield, the temperatures, they're going to get up thousands of degrees. The Apollo mission heat shields, they were 5,000 degrees. And not very many materials can handle that, and the ships will burn up. In fact, most heat shields are made so that as they're heating, they actually melt. And so they're timed so they're thick enough that part of them melt off, but you still have enough left to protect the ship when it's all said and done. So one way to use this, if you want to land on Kerbin, you can actually lower your periapsis to about 30,000 to 40,000 meters. And that should be low enough that the atmosphere will slow you down with aerobraking and actually bring you in right to land on the planet at about the right speed, not coming in too fast where you'll burn up in the atmosphere and hit the ground real hard, or coming in too shallow where you'll just kind of skim the atmosphere and then swing back out into orbit. That's about the right height there. Although, if you go in a little too high, you'll skim out of the atmosphere, and then you're just in a lower orbit. You'll come right back around again, and you'll probably land the next time. So it's not a big deal. And I'm going to throw in there the counterpoint of aero braking is litho braking. Aero, of course, meaning air. Use air to brake. Litho is based on the same root as the word for rock. And don't get me wrong, it will work. Running into rocks will totally slow you down, just perhaps in a surprisingly unpleasant manner. So you do want to remember, unless you want to do litho braking, when you do aero braking, you have to do it somewhere where there's an atmosphere. So if you did it, for example, on the moon, there's no atmosphere. Aero braking is not really a possibility. All right. So we're going to do a couple of rockets here for our next assignment, and you're going to adjust orbits and look at kinetic and potential energy. And if you've had a little bit of experience with Kerbal, I know we haven't got into this yet, but if you wanted to make a rocket where you can separate out a capsule with a heat shield on it and wanted to try some aero braking too, that's fine. Or if you just wanted to, slam your rocket into the atmosphere and see what happens to it, I mean, the Kerbals grow back when you restart the game, so it'll be okay. All right, so that's all we had for today. We'll be posting your project for you guys to work on here tomorrow, and you guys have a good one. Stay safe.